So what makes something a color such as this blue, and how can we make it a green color? And why is this green a different process to this green? And how is it that I know that this will turn purple? All right, so this first green is actually the emission spectra. And so it is emission of light. The copper is heated in a flame and the electrons are excited to higher energy levels. So when the excited electrons move back down, they release color wavelengths, as you can see here. And we use a spectroscope to break it up into the light to see the real color wavelengths. And so a spectroscope uses a grating, it's just over here. It uses a grating and a prism, and that breaks up the light to see the colors that we observe. But what you actually see is just green. Okay, so what we are seeing when we see green is our three color cones trying to make sense of the three different wavelengths, exciting the three cones to different degrees. So the brain then makes a decision to perceive that as green. For copper, there is mostly green, so green wins out, but this could be completely false. So for instance, you look at hydrogen, hydrogen looks pink because it's a combination of red, green, blue, and purple. But that's not what you see. You don't see these four different colors. Your brain has three different cones excited, and it makes a decision to tell you that it is pink, which is not correct. Okay, so in a similar sense, what you're getting here is blue, because what you're seeing is mostly blue, but it's not blue. There's some green, light blue, and dark blue, and I guess you're kind of seeing light blue as well. Okay, because if you take out these orange, so that this is a transmission of light or reflection. If you take out those reds and oranges and greens, you're only left with this cone that's working, so it's going to say blue, although that cone is picking up a small amount of green. Okay, now instead of using this complicated process, we've worked out this color wheel. So basically you can use the color wheel to get the same conclusion. So if you just draw a line straight through it, and if you're seeing blue, then you can safely assume that it's the orange wavelengths that are being absorbed. So the color will tell you which one. The color will tell you which ones are being absorbed. So an important thing to note here is the color, only photons that are the exact right wavelength to push the electron exactly from its original energy level to the next will be absorbed. And that is called, in this case, it's a d orbital split. That's the band split. So if you want to learn a bit more about this, go to crystal field theory or electronic band gap theory, and that will help you understand that a little bit more. And so the wavelengths that are not exactly able to move it from this level to this level, if it's too little, or too high, it will just pass straight through. So in the case of copper, the electrons are specifically moving d electrons between the energy levels. And this occurs because there are molecules with negative ends that are attracted to the positive copper ion, and this is causing pressure on the 3D orbital shapes and not the others. So there is the spectrochemical series, and these ones are to the right have a much greater effect at splitting these d orbitals. And it just so happens these d orbital splits are just within the perfect range of about 400 to 700 nanometer wavelengths. So that is why these d orbital elements are the ones that produce colors quite commonly. So normally copper is blue because the split is the distance that will absorb the orange photons. However, in this experiment we added hydrochloric acid, quite concentrated, so these are demos only, which is adding chloride ions. And so the split is less because it's a less strong ligand. That's the word that these species are actually called ligands. And these ligands surround the copper 2+ ion, so they're called complex ions, by the way. And so the split is less, and so the red is absorbed. And so the red's absorbed according to the color wheel. You'll see green, which is what you do. And in the reverse, if we add a stronger ligand, which is ammonia here, then the higher absorption in the yellow area is created. And if you absorb in the yellow area, then it's violet. And so that's what you see. Okay, so there are all the basic concepts of the two different reasons and ways you can see light. One's emission, one's absorption. And hopefully the teacher will now present you with a completely different transition metal. You may be able to predict the color of that, and certainly add different ligands and predict the color change then and explain it. Okay.